optimizing volume and surface area. So what we're going to do is look at optimization of surface area and volume of rectangular prisms. The first thing that we're going to do is look at figure 1 and figure 2 and see what we notice. So both shapes have the same volume, but their surface areas are different, and this shape has less surface area. And in the context of maybe even cardboard boxes, it'd be advantageous to have less surface area because it would cost less to house the same volume or same capacity. Comparing figure 2 and figure 3, the surface area is the same, but the volume of this box is larger. So for the same surface area, this configuration, 2 times 2 times 2, which is a cube, is more efficient for containing more capacity for the same surface area. So what can we take from this? Compared to all other possible rectangular prisms, a cube maximizes volume for a given surface area and minimizes surface area for a given volume. So again, it's helpful to use an image of the optimal solution to make decisions regarding optimization. So the volume of this shape, a cube, is x times x times x, length times width times height. And if you remember our prisms, it's kind of like you take the area of the base, being a square, and multiply it by the height, x. As a surface area, we have the front, back, top, bottom, left, and right faces, all 6, are exactly the same. And each one has the same area as x by x, which is x squared. So there's 6 faces, each of them are x squared. And this is the formula for this optimal shape. So we're going to use this in optimization problems. Optimizing rectangular prisms. Rosa constructs a rectangular prism using exactly 384 inches squared of cardboard. It has the greatest volume possible. So if it has the greatest volume possible and it's a rectangular prism, we know that it is a cube. What are the dimensions of the prism? And what is the volume? So, given our knowledge of the cube being optimal for maximizing volume and minimizing surface area, we're going to look at the information given in the question. 384 inches squared is a surface area. So we're going to use a formula which has surface area within it. So surface area of the shape is 6 times x squared, and then substitute in the value for surface area. That's eliminated a variable in the equation, and therefore we can solve for the variable x using opposite operations. So namely, divide each side by 6, and then take the square root of both sides. And then we've isolated our variable x, which is 8 inches on one side. And the question is asking what are the dimensions of the prism. It would be 8 by 8 by 8 because it's x on each side of the cube. And the volume is equal to x cubed because length times width times height for the shape. So 8 times 8 times 8 is 512 inches cubed, and that's the greatest possible volume. Next, the opposite information is provided. In this last example, we were given surface area, but in part B, Liam constructs a rectangular prism with a volume of exactly 1,331 meters cubed. It has the least surface area possible. So if it's a rectangular prism and it has the least surface area possible, that indicates that it is in the shape of a cube. What are the dimensions of the prism, and what is the surface area? Again, make sure that you draw an image so that you understand each step. That when you're using your equations, you're looking at this shape to derive the formulas, even if they are provided. Think about it for yourself. In this question, a volume is provided. So we should talk about the volume of this shape, which is x times x times x, that's x cubed. The reason why we selected a formula involving a volume is because then we can substitute this into the equation, and then we've eliminated a variable, and can solve for the remaining variable x. The opposite operation of cubing is the cubic root. So we take the cubic root. This should have a 3 on it. Let's change that. And then we end up with 11 meters. So the dimensions of this are 11 by 11 by 11. It's a cube. And the surface area is 6 times x squared. Again, think about this shape. Each of these faces is x by x to calculate the area. And there's 6 of them, just like a die. So 6 times x squared is 6 times 11 squared, which is 726 meters squared. So we found the greatest possible surface area for this volume. Now, what we're going to do is look at a quick summary of what this looks like graphically. In the previous example involving the optimization of rectangles, where we learned that the square minimizes the perimeter and maximizes the volume. In this case, just to show the capabilities of Microsoft Excel, what I did was think of each and every single possible face that there is that you could have for x and y. And then if you know this constraint, we said volume is equal to length times width times height. And the volume is, for this problem, we're told that it's 100 meters cubed. Then we can find an expression of z in terms of the other variables by isolating the variable. So then we can figure out what z is. And in this table, we have various values of x and this values of y. And what we can do is calculate the surface area. So this is quite advanced as far as Microsoft Excel is concerned. But what we're going to do is just talk about this quickly. These dollar symbols in this equation allow us to lock in specific components of our reference. This is the locking in. It's a locking in the column for F, and the case here is locking in the row. Okay? So regardless, we were able to get the surface area for each of the different configurations of x and y, because that would dictate the value of z. And this is what I'm getting at. The shape for the optimization of a rectangle and a square was a parabola. But in this case, for a 3D object, we have a 3D solution. We have a curve. And that curve is telling us what the solution would be. Now, we know that if the volume is 100 meters cubed, then the optimal shape would be a cube root of this value, which is approximately 4.6. You can see here that the minimum surface area is occurring between, is in this neighborhood for surface area. But as a shape, the whole take home of this right here is just that the lowest point on this graph for surface area is the point which minimizes, or the configuration of the rectangle which minimizes the surface area.